Hi Rockridge, this is Mrs. Berger, and today we'll be talking about logs and exponentials, or logarithmic and exponential functions. So the first thing I want to talk about is the algebra behind this, and then we will talk about the graphing. So the definition of logarithm with a base of b, so that's what we're looking at here. We're looking at log base b of y. This is logarithmic form. This is logarithmic form. This is exponential form, y equals b to the power of x. X is in the exponent, so this is exponential form. So if we ever ask you a question and say, put this in exponential form, your answer needs to look like this. And if we're asking you to put something in logarithmic form, you should be looking at something like this by the time you're finished. Now, we have common log, where this little base right here is 10. And that is the log button on your calculator. So here's the log button on your calculator. This one right here is what we use for a base of 10. Log base 10. There's also a button on our calculator that gives us a base of e automatically. That is the natural log of x, or ln x, and that is found on our calculator right below, right here. For any other base, if you don't want a base of 10 or you don't want a base of e, you will go into your math menu and you'll go very close to the bottom here, log base. That will get you any other base. If you want a base of 3, you'll put a base 3 there, okay? So that's where you'll find the buttons on your calculator to help you with this. And just to remind you, you can jot that down. Any other base, use log base in the math menu. Okay? So let's get down to what we mean by converting these things from log to exponential form. So you'll be faced with something like this. If we ask you to rewrite this statement into exponential form, what we mean is, if this is the base, this base to the power of 3 is 64. 4 to the power of 3 is 64. So this is a rewrite of this statement. This logarithmic statement has been rewritten into exponential. Similarly, we take this base of 2 raised to the negative 3 power is 1/8. 2 to the negative 3 power is 1/8. And we know that's true because 2 to the negative 3 power, that just means 1 over 2 to the 3 power, right? So that's why that's 1/8. Example 3, a log with a base of 1/3. 1/3 raised to the negative 1 power is 3. 1/3 raised to the negative 1 power is 3. And we know that because anything raised to the negative 1 power just means we flip our fraction, right? So that's converting from logarithmic form into exponential form. Now let's go the other way. So we know if we're going from exponential into logarithmic, we know two things are present in our final answer, the word log and an equals sign. And remember what happened up here. This base right here became the base that was being brought to the power, right? So the little curly part of the g has the base. So in our case down here, that would be the 8. And remember the 4 was being raised to this power on the equal sign, on the other side of the equal sign. So 4 to the power of 3 in this case, 8 to the power of 0 in this case, 8 to the power of 0 equals 1. That's how you would convert between exponential form into logarithmic form. Let's do it again. Let's start off by having a log and an equal sign. We know the 5 goes by the curly part of the g to be the base. 5 is being raised to the power of 3, and we would get 125 as the answer to that question. Let's look at example 6. We set up our log and our equals sign. This right here is the base, so that goes with the little curly part of the g, that's the base. And that base is being raised to the negative 2 power, and the answer to that question is 64. So So that's how we convert from exponential to log. So if you're doing your homework, make sure that you have this note in your mind. When you see something like this, the question this is asking is, 4 to what power is 64? That's the question that's being asked with this problem. Log base 4 of 64 means 4 to what power is 64? So for instance, if we had something like this, we need to know what this equals. What does this equal? We're saying 2 to what power equals a half? Well, if we were to look at, sorry, that's a question mark. If we were to look at 1/2 to be into a base of 2, think about it this way. 1/2 is the same thing as 2 to the -1. So this question mark must be -1. So the answer to this question, 2 to what power equals 1/2? 2 to the -1 power equals 1/2. Similarly, in this question, 4 to what power? 4 to what power equals 1? 4 to what power equals 1? The only thing that could bring this to 1 is if the question mark equaled 0. Now, we can also use our calculator to help check ourselves. Remember log base? Well, let's pull that up again. That was Math Menu, log base. Let's look at our first example we just looked at. Log base 2 of 1/2. 1 divided by 2. We got -1 for our answer, and so did the calculator. So we can always check ourselves with this. So remember, y equals b to the x, the exponential form, is the inverse of y equals log base b of x. So if we're ever asked to find the inverses of these things, we can use our properties to calculate this. Let me show you. Let's say we're asked to find the inverse of this function. Remember what we had to do for inverses? Inverse meant swap x and y. So let's swap x and y first. X equals log base 2 of y. Now, whenever we did inverses, we not only swapped x and y, but then we had to solve for y. How would we solve for y? Well, if I write it the other way, if I write log base 2 of y equals x, does that clue you in as to what we're going to do? We're going to use this tool that we just learned about 2 minutes ago. We're going to use this our brand new tool to get y out of there. We're going to take 2 to the x power and make it equal to y. 2 to the x power equals y. Now y is all by itself. And remember, to find the inverse, we swap x and y, we solve for y, and we put proper notation. We put proper inverse notation on that and declare that to be the inverse. That's a -1. So let's do this again. So number 2, let's first remember what number 2 should be written as. Natural log, remember what the base was for natural log? This problem is the same as log base e of 6x, natural log. So now that we have that rewritten that way, let's go ahead and do our swapping. Let's swap x and y. Let's make it x equals log base e of 6y. If you need to, you can rewrite this with the x on the other side, just so you can look at it the way we have been. So that way I just swap the sides of the equal sign so that I can use my rule e to the x power equals 6y. E to the x power equals 6y. Now y is not yet all by itself. We're going to do one more step to make y by itself. We're going to divide by 6 on both sides. So e to the x over 6. Now that y is by itself, we can give it its inverse notation and declare this to be the inverse of problem number 2. Now we're going to go from an exponential to a log because we need to find the inverse of this guy. So let's first swap x and y. So let's make this x equals e to the y minus 2. And in order to get this out of there, we need to put this into log form. So if it helps, you can swap the sides of the equal sign again, if that helps you look at it this way. But we're going to do log base something equals something, right? The base is this number here at the base. The power is the answer to the question. And this becomes this. Y is not yet by itself. It's almost there. It's not quite by itself. Let's add 1 to both sides. Oh, and you know what? Instead of writing log base e, let's make this natural log, because that's proper form. So let's make this proper form natural log of x. And let's give this its proper -1 notation to declare this the inverse. So you're not going to do very many conversion questions. You'll use your conversion skills to find the inverse. So very few times will you be asked to simply convert from exponential to log and log to exponential. You're going to use those those conversion skills to find inverses. All right, let's take a look at these, simplifying the expression questions. I'm going to clear the board because I've run out of room. So let's clear the board and look at this question here. So to simplify this, we want to know what the answer is to this question. Let's convert. 2 to some power equals this answer. 2 to some power equals 2 to the x plus 1. Well, that means the answer, the question mark, must be x plus 1. Now, I tell my students, you can either run through the mechanics of the conversion like I do, or you can memorize these facts. Log base b of that same number b to the power of x, the answer is always x. We did see that come out here. That did play out here. I always like seeing the mechanics of it, though. So I'm going to walk us through the mechanics. If you would like to memorize these two facts, that's perfectly fine. You don't necessarily have to walk through the mechanics if you just remember this. So let me walk you through the mechanics of the next one. We don't know the answer to this. We need to know 3 to what power is the same as this. 3 to what power is the same as this. Well, we don't yet have these to be the same bases, which is what we had in the first question. We need to make sure that they're the same bases. But we could get 9 to be the same base. 9 is just 3 squared. So we could rewrite this as, instead of 9 to the x, we could make this 3 to the 2x. In which case, the question mark, the answer to this question, must be 2x. Okay? So make sure you do have the same base before you answer these questions. Notice that has to be true here for your memorization as well. So make sure you convert to the same base before you answer these questions. All right, now we're going to go from an exponential. Believe it or not, this is an exponential. It's a base of 5 being raised to this power. We're going to go from an exponential to a log to solve what this one equals. So let's set up our log and our equals sign. This base always goes by the curly part of the g. So 5 to what power? That power is here. This whole thing is the power. So 5 to what power equals the question mark. So that means question mark must equal x minus 1. Or you can memorize this, which is what we just did here. I like the mechanics. I'm just, let me see how it mechanically works, but if you don't like the mechanics, you can certainly go ahead and just memorize this fact here. Just make sure you've got log to the same base as what's here. This and this have to match. All right, so that's the algebra behind logs and exponents. Now let's take a look at the graphing. To keep the video as short as possible, I'm going to go and run through not every single part of the notes, just to get you on the right track for these things. So graphing exponentials, we'll do exponentials first. And again, you know you've run into an exponential if you have x in the power. So y equals 2 to the power of x. This has got to be an exponential function. And if you would just input some different values for this and sort of hack your way through this mathematically, you would see how this behaves. So if you were to input -2 in for x, you would get 1 over 4, right? And so therefore the point -2 positive 1/4 is on this exponential. If you were to input -1 here, 2 to the -1, that's 1/2. So -1 comma 1/2 is on here. If you were to raise 2 to the power of 0, you would get 1, so 0 comma 1 is on this. 2 to the power of 1 is 2, so 1 comma 2 is on this. So you'll start to see that this function looks like this. This is an exponential. This is what an exponential looks like. Okay? And notice that even though we can keep going negative on x's, 2 to just a really, really large negative number is just a really, really small decimal, really, really small fraction. You'll never actually get an output of 0 here. You'll never be able to raise 2 to any power that will ever get you to 0. So this comes close to 0 but never reaches it. The domain of this is all real numbers left to right. The range of this is 0 to infinity, not including the 0. It's 0 to infinity because it never gets down to that 0 and it never goes below. You could also write this as y such that y is greater than 0, but not equal to. We don't have a vertical asymptote. We do have a horizontal asymptote at this axis, right? It doesn't go below 0, so y equals 0 is the horizontal asymptote. We are increasing the whole time. We're going up, 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 up the whole time across all real numbers. Another way we could write this function is y equals 1/2 to the negative x. Remember, 1/2 to the -1 is just 2. So another way you could write this is 1/2 to the negative x. So if you were on a test and anybody asked you, out of the following choices, which of the following is the same as y equals 2 to the x, you could say, oh, this is the same as y equals 2 to the x. 1/2 to the negative x is the same function. Let's look at what happens if we have 2 to the negative x. If we were to put values in for x, just like we did before, if we put in a -2, you'd have 2 to the -2, which is 4. So -2, comma 1, 2, 3, 4 is on this. 2 to the -1 is just 2. So -1, comma 2 is on here. 2 to the -0 is 1. So you could have 0, comma 1 on here again. Now let's just do one more. 2 to the -1, that's 1/2. So 1, comma 1/2. So again, we have this type of behavior here, and it will skirt along here and have like an infinitely small fraction. This red one was called exponential growth. This blue one is called exponential decay. Left to right, it's getting smaller and smaller. The domain is still all real numbers. The range is still 0 to infinity. There is no vertical asymptote. The horizontal asymptote is still y equals 0. It's going to get close to 0 but never cross. It's always decreasing across all real numbers. And this guy could be rewritten as y equals 1/2 to the positive x. Instead of 2 to the negative x, you could have 1/2 to the positive x. So that's why these things work the way they do. That's just using the algebra to explain why they work the way they do. Now let's dig into how we would translate these. If you noticed already, there was one point that appeared on both of the exponentials we just looked at, and that was 0, comma 1. We'll use this as a reference point, as a starting point for our shifts. We'll also use the asymptote y equals 0 as a starting point. That's our baseline. And we're going to move from these as we shift. So the a's value, a, h, and k, we're going to revisit a, h, and k, like we did for past things like quadratics and absolute values and several other functions. We used a, h, and k. Here's what our exponential function looks like. And remember what these things were in charge of. A is in charge of making it narrow or wide. That was our dilation. H is in charge of left, right. And k is in charge of up, down. Just like our other functions. So let's look at who we have here. Y equal 2 to the x plus 1. The x plus 1 indicates we've got an h of negative 1. Since there's nothing out front, we assume there's an invisible 1 there. And since there's nothing out here, we assume k is 0. So that means we have no up-down, we have no narrowing or widening, we just have a left 1 shift. So if our starting point of 0, 1 was here, and our shift is a left 1, our new reference point is negative 1, 1. Our asymptote was at y equals 0, and if we shift left 1, that does nothing to this asymptote. Shifting left 1 does nothing to it. It's not going up or down. So our asymptote stays the same, y equals 0. Our domain, and let me draw that in. So here is our asymptote. And this exponential acts like this. Our domain is all real numbers, as is every exponential. And our range is 0 to infinity, not ever reaching that 0. End behavior for these is interesting. As x goes to negative infinity, y does not go to negative infinity. It does go down, but it never goes any further than 0. It approaches 0 forever, to the left. On the right, as x goes to positive infinity, we are allowed to go up as high as we want to infinity. For reasons for time, I'm going to skip this base of e. You can take a look at that on the notes. But let's look at maybe number 3 as our last exponential example that we'll go through here. So number 3, we don't have anything being multiplied out front, so it's an invisible 1. Our h appears to be a 3. And our k appears to be a negative 3. So this reference point that used to be 0, 1 has been shifted right 3, 1, 2, 3, and then down 3, 1, 2, 3. So this is our new reference point. That would be 3, negative 2. Our asymptote, which used to be at y equals 0, has been shifted down 3, 1, 2, 3. So our new asymptote is y equal negative 3. This exponential acts like the others. Our domain is still all real numbers. Our range is slightly different. It goes from negative 3 up to infinity, not including the negative 3. Our end behavior, as x goes to negative infinity, y does decrease, but it never decreases past the negative 3. On the right-hand side, as x goes to positive infinity, y is allowed to go to positive infinity. Number 4, I'm not going to do the whole thing for you, but and of course you can always put these in the calculator to see how they act. You will shift this reference point using the hk values, and you'll also flip it because the a for this one is negative 1. So you'll see a function that it acts like this. It's an exponential decay. Since there's a negative 1 here, it's an exponential decay. So you can certainly pause the video and run through those and check against the key if you would like. Additionally, we've got some dilation factors here. We've got a 3 dilation factor here, but no shifts in left, right, or up, down. And then, of course, number 6 is the most complicated. You've got a dilation factor as well as a shift left, right, and a shift up, down. Now, this dilation factor, since a equals 3, h equals 0, and k equals 0, what you'll do is, since you have a reference point of 0, 1, you're not shifting left or right or up or down, but you are multiplying the y value by 3. So you'll multiply this y value and pop it up here to 3. So it'll be 0, 3. Okay, so that's what happens with a dilation factor. Make sure that you do your shifts left and right, up, down first, and then only apply your a value, your dilation, to the y value. Okay, and so this will act as most of them do, and you can answer questions about that. So go ahead and try those. If you need to pause the video, go ahead and do all of those and check against the key, but in the interest of time, I'd like to move to logs. So for log functions, so let's remind ourselves, exponential functions, have an asymptote of y equals 0 and a domain of all real numbers and various ranges. For log functions, we have an asymptote of x equals 0, various domains, but a range of all real numbers. Because remember, when we're told that these are inverses of each other. And inverses of each other basically means that you are reflected about this line, y equals 1. And so, you look like this for a log function. This is exponential, this is log. And they are reflected across this line, y equals x. So we are now going to focus on functions that look like this. Again, they have vertical asymptotes, not horizontal asymptotes. They have limited domains, but not limited ranges. So we are always going to take a look at logarithmic functions looking at asymptotes. So find the asymptote. We start out with a function that has an asymptote of x equals 0. If the bases aren't 10, then we flip the table of values. If it is, then you go ahead and use the calculator to find our values. And our reference point, instead of 0, 1, it is, shocker, 1, 0. So that's our starting point. So any shifts are going to happen on that. And here's our standard function, y equals log base b of x minus h plus k. And I should put an a in there. So my a is my dilation. That's my widen or narrowing. My h is my left-right. And my k is my up-down. And again, all of that with respect to a starting point of 1, 0. So let's see how this plays out. Let's first identify a, h, and k. In this case, we've got nothing in front of here, so we'll make a 1. H is a 2, and k is a 0. Remember what my reference point was. It was 1, 0 to start with. And with an a of 1, an h of 2, and a k of 0, it looks like we're only going to go right 2. We're not going to go up or down, and we're not going to multiply by any factor. So that means my new starting point is 3, 0. Now, my original asymptote was x equals 0. So my new one will move right 2 and become x equal 2. So that is my new asymptote, x equal 2. Nothing's going past there. This function will look like this and skirt alongside here. My domain is limited. I only have x values starting at 2 and going to infinity, not including the 2. It will never go to the left of that line. My range, however, goes forever down and forever up. Now, careful when you're looking at these on your calculator. A lot of times it will cut off the values. This function should go forever down, regardless of what your graph on your calculator looks like. Now, on the left, take a look at what happens on our left-end behavior. As x goes to the left, it does not go to negative infinity. It only ever reaches a negative 2. As it approaches negative 2 on the left, my y values are going down to negative infinity. On the right, it is allowed to approach positive infinity, and as it does, y also is allowed to go up to positive infinity. This one should be written, apologies for this, it should be written log base 2 of x minus 3. So that's what that function should look like. So you have an a of 1, an h of 0, and a k of negative 3. And again, your reference point is 1, 0, so it looks like you'll only be going down 3. Our asymptote will not change, it will not go left or right. So I'll allow you to do number 8 on your own. In the interest of time, let me go to a more complicated one with a lot of things going on. Let's take a look at 9. So let's identify a, h, and k. There's nothing out front, so let's assume that a is 1. H is negative 1 from here, and k is 2. So again, our reference point started at 1, 0. Let's go left 1, up 2. That's our new starting point. 0, 2. Let's take a look at what happens with our asymptote. Our asymptote was originally here at x equals 0. An up-down shift of 2 does nothing, but a left of 1 puts us at x equal -1 for the impact on the asymptote. You'll be asked to make sure that you document and draw all of these things in. So make sure you can document and draw your asymptote and go ahead and show your function approaching that asymptote. Our domain, therefore, never goes to the left of -1, so it's -1 to positive infinity. Our range, however, for this log and all logs is all real numbers. On the left, as x goes to, it's only ever allowed to go to -1, but as it does that, y, or f of x in this case, goes to -infinity. On the right, as x goes to, it is allowed to go to positive infinity on the right, and as it does that, f of x goes to positive infinity. I will let you go ahead and take a look at the key for log base e, and it behaves slightly differently. You can always use your calculator to help you with those natural logs. But go ahead and attempt your homework and get some practice on this, and let us know if you have questions.